Hello, I am Dr. Paris R. Von Lockett, and today I'll be talking to you about stress concentrations. It's a topic straight out of solid mechanics, sometimes in advanced solid mechanics, mechanics of materials, very relevant to engineers, especially practicing engineers who design parts and who fabricate parts. Okay, this lecture focuses on how stress concentrations rise and how nominal stresses are affected by those stress concentrations. So our topic, stress concentrations, and after this lecture it's important that you are able to determine where stress concentrations might arise, and if given multiple geometries, determine which ones would have higher or lower stress concentrations, and also understand how to identify and calculate net cross-sectional area properties. How do we find that net cross-section, and then how do we calculate its properties? Okay, real beams, as you might imagine, especially shafts, have non-uniform sections. So here on the right, we're showed a step shaft, which might be part of some sort of drivetrain. You might have keyways. There can be bolts. Bolts actually have a shaft, a shank, and they have a thread, which has higher and lower sections on it, depending on how it's cut. And it also has a head, which is different size than the shank itself. And so it's natural for these different geometries to exist on a fixed part. And as this part is loaded, we have then transitions between those geometries which affect the stress state. These cause localized stress concentrations. These stress concentrations arise because if you consider axial stress or stress along the dimension of the shaft or the beam to be these sort of flow lines, they get crowded when you reduce the section geometry. And the rate at which you reduce that section geometry can affect the degree of crowding. On the left, we've shown a step, and that step will have more crowding and therefore higher concentrations. On the right, we've shown a fillet, and that fillet has less crowding and will therefore has less concentrations. So that type of transition is important. It's an interesting thing to note that you can actually visualize stress concentrations. You can do them using experimental methods. You can also do them using FEA methods. So here we're showing the stress concentration introduced by notches and fillets and a flat bar subjected to a bending moment. So as you can see here, we've got a moment M. This is the nominal distribution of that bending stress, which is linearly varying from bottom to the top. It's the highest at the outermost fibers, but you see here, these outermost fibers are actually inset from the outermost fiber of the entire shaft or beam due to this fillet. As we look at closer to the notch, as we look at the distribution of the actual bending stresses, we see that they're not necessarily linear. They actually taper off in terms of their asymptotic value near the ends, and so there's a different profile that occurs. On the bottom left, you can see the result of a photoelastic stress analysis, and in this case you have what's called a birefringent polymer. This means that if you shine light through it, as the light passes through the polymer, it's affected by the stress state of the polymer. The photons actually interact with the molecules, which affect it as it's passing through, and you can polarize the light somewhat based on its degree of stress. And then if you are using polarized light in the first place, those two polarizations will actually interact. The polarization it comes in at, and then the shift of the polarization because of the local stress state will change the color as the light as it goes through. It's kind of cool. I used to do these experiments a lot when I was in graduate school, and so it's a method that I'm very familiar with, and also I used to think was a lot of fun, although very time consuming. What happens, you see in these colors, is that the stress as it varies will shift from one color to the next. Here we're showing light and dark. Sometimes, depending on how you filter it, you can get grayscale, you can get color patterns, but here they're just showing light and dark patterns. The thing to point out is that within these patterns, you have what are close to isobars, not necessarily strictly isobars, but these are regions of somewhat uniform stress as it transitions from one level to another. On the right, on the finite element method, we can show our stress concentrations around our notches and around our fillet. And here we're showing true isobars because we can plot them numerically. Every line is a level of constant stress, and as you can see, they get more and more compacted as you get closer to the actual hole, and here more and more compacted as you get close to the fillet. So what's the goal here? The goal here is, if we know what the stress looks like experimentally, and we then recreate that numerically in our finite element method, we always want to make sure that the finite element method can return to us good stress values so that we know it's a good approximator of our solution. So experimentally then, how do we go about calculating what these stresses are? Well, it begins with our stress concentration factor here, KT, which accounts for geometry. So the geometric stress concentration factor for normal stresses is the KT as shown. It's KTS for shear stress, and these scale up either our maximum normal stress sigma or our maximum shear stress tau as shown. So we have a nominal stress multiplied by KT and normal stress, or a nominal shear multiplied by KTS. Now it's important to point out that sigma nom and sigma t nom, tau, the nominal shear stress, are calculated for the particular applied loading and net cross section. I'll show you what that means on the next slide, assuming a stress distribution across the section that would be obtained for a uniform geometry of that net cross section. So imagine that the cutout or the notch or the fillet isn't there, and you have a section that's only as wide as the material that remains. Okay, so let's take a look at the top right. We'll see what that looks like. Here we've got our cross section again. We've got our cutout, our notch. We've got our fillet. And what's going on here? Our distance for the base part is capital D for our width, but we have this inset. Our notch height is H, which means that we have a reduction of our D value across the whole notch by 2H, or we can just call that some nominally new D of small d, which would be capital D minus 2H. What's the point? Well, the takeaway here is that the nominal stresses are calculated using this net cross-section. So it's reduced by our notch geometry, which means that our cross-sectional properties of I for our moment of inertia and the area are then found with this new D. All right, once we have those new cross-sectional properties, and I should also point out our new C value, because C only now goes out to D. This C, our outermost fiber, has its maximum normal stress here, and not all the way up at the outermost of the whole part, because in that section that doesn't exist. We would then scale the geometry or the stress from that geometry by this KT. So our nominal stress here, MC over I, where C and I are calculated on the reduced area, and then we would scale that up by KT to find the maximum. Again, these consider how the part behaves. They don't consider how the material behaves, because some materials we know are actually strain hardening. When you overstress them, they actually have a stiffer response than normal, and some materials are actually strain weakening. So that has to be taken into account based on the type of material you're working with. All right. Well, hopefully you've learned a little bit about stress concentrations. Maybe this was a bit of a refresher for you. If so, great. If not, just really hone in on those ideas of what is that net area. It's that reduced cross-section from which we can calculate our areas. We can calculate our moment of inertia. We can calculate our C values, our outermost fiber values, etc. All right. Thank you for participating. Thank you for watching. And we'll see you in the next lecture, where we begin to sort of analyze this problem by hand, and then beyond that through SolidWorks. Thanks, and take care.